Now, to introduce coordinates, let me start with a simplest case of one dimensional coordinate systems. Okay. Let us assume that I have an infinitely long parallel road, okay, which is running along this way, and there are houses situated along the road. Okay. You can imagine a highway or something where the road is long and there are houses situated along one edge of the road. Okay. Now, any road could be taken as a reference because this is an infinitely long road, there are an infinite number of houses and you can take any house as a reference, but it might be very easy for me to take my house as a reference. Okay. So, I will take my house as a reference and I call my house as house number 0. Okay. Of course, I could have called this house as 150 or 200, it does not matter, but 0 seems to be an giving you a nice intuitive feeling that this is the origin, this is the reference. So, the reference could be set to 0 and I take my house number to 0. Okay. Now, what I start doing is there are different houses along the road, I start labeling all these houses, right. So, I label the houses 1, 2, 3, 4, 5. For example, my friend's house happens to be 150th house from my house. Okay. So, this friend's house is 150th house from the reference house which is my house. So, I label them as 150, then I have 151, 152 and so on, and it will continue like that. There are houses to the left of my house as well. So, I will label them also 1, 2, 3, 4, 5. Now, if I say house number 5, you would be confused. Why would you be confused? Because I am not specifying whether this house number 5 is to the right of my house or to the left of my house, right. So, once I fix the reference, I also need to specify the direction in which I have to find this house. So, if for example, we have a mutual friend and I want to direct that mutual friend to one of my other friend's house, right, to my friend's house which is at 150 to the right of my house, I have to specify go along right of my house and stop at 150th house. Okay. So, I have to specify both direction as well as the distance or the house number which I have to go. So, this is a one dimensional system. Now, we can mathematically represent them, that is we can convert this housing analogy to a coordinate system by drawing a line, and we label this line as x axis, and we call this point, say my house, as the reference house with a number 0. So, I associate my house with 0 and then I start numbering all the other houses. The house, to distinguish between houses to the right and houses to the left, I can say the houses to the right are positively numbered and houses to the left are negatively numbered. So, the house number 1 which was to the left of my house has now become -1. Now, I do not have to specify go to the right or go to the left, I just have to specify -150th house or +150th house. Maybe there is a house in between 150 and 151. This house could be 150.5. So, I could say hey, go to the location of 150.5. Maybe there is a landmark at 203.5 or 203.8, right. So, I could then say go to the landmark 203.8 or go to the landmark at -153.6, right. So, I can specify that, and x is the axis that I would be calling. Okay. So, what this house analogy has told you is that I can associate on this road any point, right. I can specify that point by giving it a number. So, I have converted or I have found a method in which I can locate a point in space by a number. I can specify that point in space by a number. For example, the position of the nth house can be specified by giving a number n. Now, let us say I have a friend, okay, who does not agree to consider my house as a reference. I mean, everyone would like to consider their house as the reference. So, I have a friend who wants to consider his house, which happens to be house number 1, as the reference. So, what he or she does is that they keep this house 1 as the reference house. Okay. So, in their coordinate system or in their method of measuring the locations or specifying the locations of houses, 1 becomes 0, n becomes n minus 1. Does that mean that the nth house has actually physically changed? No, the house is situated where it was. Its number that we are specifying has become different, because in my mind 0 is the reference house and for his coordinate system 1 is the reference or 1 is the 0 for that one. So, because the origins are different, the number that we come up with are different, but physically this is the same house. The house has not changed just because I decided or my friend decided that the origin needs to be different. Okay. So, I hope you get the difference between specifying a coordinate system and specifying a number. Okay. This is closely related to the fact that vectors, we will soon see how to connect vectors here. So, this is closely related to the fact that vectors are independent, whereas the number that we associate with a vector is dependent on the coordinate system that I choose. So, now how do we associate vectors to this coordinate system? So, we have already established a coordinate system, okay, and let us say the coordinate system that I have established should allow me to measure distances. So, I do not want to say the position of 150th house, I want to say, hey, my friend's house which is at 150 is actually at 150 kilometers, or it is at 150 meters, or it is at 150 centimeters. Okay. So, there is a landmark at 203.8 kilometers. So, I want to specify distances out there, but you see what I did over here, I had a distance of kilometer, meter, centimeter. How was this distance or how was this unit of measure formulated? Let us look at this. I have all these houses, it is again, see that I am using my coordinate system. So, I can use my coordinate system and say I measure the distance from my house to my next house along the right, which is say 1, and I call this as the unit distance. So, all other distances along x axis are now measured in units of this distance. Okay. So, this is 1 unit. So, 150th house will be 150 units away from 0. Again, there is no specific reason why we have to specify this as 1 unit distance. I could specify the distance between midway from my house to my friend's house or to my neighbor's house as 1 unit, then the 150th house which is my friend's house will be at a distance of 150 into 2, which is 300 units if I half the unit. So, it is clearly in my control as to what I should call as a unit, and we pick whatever the unit that would correspond to us and we just stick to that unit, and this kilometer, meter, centimeter are all the choices that we make. So, if I take 1 kilometer as the unit, then all the other distances can be measured and will be measured as some multiple of kilometer. That multiple need not be integral, it need not always be 1 kilometer, 2 kilometer, 3 kilometer. A landmark could be at 0.23 kilometers. Okay. So, I hope that that distinction is very well understood by you. Now, this is a coordinate system. Along to the right there is x axis. I have also obtained the units on which I am going to measure. Now, how do I define a vector? Consider the nth house. Okay. I can specify the nth house by giving its distance from the origin being my house which I am taking as the origin or the reference. I can give the position of this nth house as n units away from 0. I can equivalently draw a vector whose length is n and whose origin is at 0 and which terminates at n. So, this now you can imagine that I am first removing the coordinate system. I just have a vector which is lying horizontally of this length 0 to n, okay, I mean of length this line, and now if I want to attach a coordinate system, I can simply imagine a coordinate system over here in which the origin coincides with the tail of the blue vector, okay, which is what the vector n is. Okay. So, this vector n can be represented as n times x hat. What is this funny looking x hat over here? X hat tells me a unit vector along the direction of x. What is a unit vector? It is a vector which has unit magnitude and points in the direction of the coordinate system. Here I have a one dimensional coordinate system along x. So, this is pointing along x direction, has a magnitude of 1. So, this unit vector I have indicated by this orange colored vector. Okay. So, orange colored line arrow is a unit vector, and if I take a unit vector and multiply it by a number n, then I get the vector n which has a magnitude of n, and it will now be pointing along the x direction. Okay. So, now I have shown you two two things. One, there is a position which is the location of the space along the x axis that can be specified by giving it a number. So, if you imagine that there is no vector over here, if you imagine that there is no vector here, but just a number n that is sitting here on the x axis, then the location of this point where n is sitting is n. Okay. You can have another position which would be m, which would be along the x axis. Now, I have a vector with no specific reference to the coordinate system. However, I can introduce a coordinate system and say that this vector can be represented as n x hat, where n represents the magnitude of the vector and x hat represents the direction of the unit vector. So, in this case the unit vectors can only be directed along x. Now, suppose I want to represent a vector which has the same magnitude n, but it will be pointing in the negative x direction. How would I represent that? All you have to do is you have to represent this as minus n x hat. You could of course take a unit vector which would be pointing in the negative x direction. You can call that as some minus x hat. Then I can multiply that by the required magnitude, say that value of n, and then obtain minus n x hat. What we prefer to do is that we keep the unit vectors fixed. If I want to refer to a negative direction, I simply multiply that one by a signed number. If the signed number is positive, it will be pointing in the same direction as the unit vector. If the signed number is negative, right, the multiplier is negative, then it will be pointing in the opposite direction. Okay. So, this was the one dimensional coordinate system, a vector n. So, let me recap this. A vector n which is starting at origin O and ending at a point n is given by n x hat. Please note the notation that we are going to use. This will be the notation that we will be using throughout our study. Okay. Here the number n, which can be positive or negative, okay, if we associate a sign along with this one. If I do not have, then n is a positive number. So, n is a magnitude of the vector n and x is the unit vector along x axis. If I want to represent a vector which is acting along minus x direction or which is along the negative x direction, then I have to assign a sign here. Okay. I have to say minus n x hat, which will then point to a vector whose magnitude is n, that is whose length is n, but it will be acting in the minus x direction, negative x direction. Okay. If I take a unit vector and then multiply it by any number, I am essentially stretching the unit vector. Okay. If the multiplier is less than 1, then I am compressing the vector. If the multiplier is equal to minus 1, then I am taking the vector and changing the direction from plus to minus. Okay. Now, let us go to two dimensional coordinate system. Whatever fun we had to have with one dimensions is all over. Now, let us go to two dimensional scenarios. Okay. Now, here again the notion of coordinate system as well as the vector will be different. Okay. So, you can have a vector which is independent of the coordinate system, and then you choose a coordinate system such that the numbers that you get will be unambiguously defining a vector and it will be simpler to work with. So, you have an unambiguous definition of a vector in the chosen coordinate system as well as a easier method of handling the numbers. Okay. Just to bring out the distinction, look at this figure. You have a vector which I am calling as vector A, which is given by red colored arrow over here. This red colored arrow, as in the previous vectors, will have 2 points. There is a starting or the initial points. Because this is a two dimensional coordinate system, you might expect that every point in the position will be specified, position in space will be specified by 2 numbers. So, this origin point of the vector A will be specified by 2 numbers, xi and yi. Similarly, the end point of the vector will be specified by 2 numbers, which are xf and yf. Okay. What are these x and y? These are the 2 lines or the directions which are needed to completely specify any point in the coordinate system. In the two dimensional system, I have to specify the location of any point by 2 numbers, one along x and one along y. Imagine that I have this plane and then there are houses scattered all over. Now, if I want to reach a house which is at some particular point in this space over here, I can say, hey, go along horizontally 10 units of houses or 10th house, and from that house go vertically to 20th house to reach the house which is numbered 10, 20. Okay. This is the meaning of giving 2 coordinates, and you can notice that the directions horizontal and vertical are perpendicular to each other. We will talk a little bit about the requirement of perpendicularity later. Okay. At any point we can be considered as origin, so we consider this point O as the origin here. So anything to the increasing side of x will be positive, this would be positive. If you go below this line, you will be going along minus y. If you go to the left, you will be moving along minus x direction. Okay. So any point in this two dimensional space or a plane can be specified by two numbers. Okay. So here is a vector A with its initial and final points. Here is a coordinate system that my friend has come up with. Now every time I specify the vector A, I have to specify both the initial as well as the final points. Now this might become little tricky, okay, because every vector needs to be specified by 4 numbers now, one for the starting point and one for the end point. On the other hand, it would be wonderful if I take the same origin, okay, for all the vectors. What am I getting by doing so? I am eliminating this need of specifying this xi and yi all the time. I do not have to specify xi and yi all the time. If I choose my coordinate system as coinciding with the tail or the origin of this vector, but the coordinate system does not seem to be coinciding, what is the solution? I cannot move the vector. Of course, I can move the vector, but normally what we think of is we do not move the vector, we move the coordinate system. There are two equivalent ways of doing the same thing. Either you move the vector parallelly until you reach the origin of the coordinate system, okay, you can do that one, or you simply move the coordinate system until you reach the origin. And moving the coordinate system not only means parallelly moving them, you can also twist and rotate the coordinate systems. Okay. Some of these things will become important later. At this point, let us not clutter too much about that. So what I am going to do is that I am going to redraw my lines y and x such that the origin of the coordinate system O, right, coincides with the origin of the vector A. Thus a vector A will now be specified only by 2 points x and y. Why? Because this 0 and 0, the origin is implicitly understood. If I had another vector, I could draw a line from the origin to the other point, and that other vector could also be specified by only 2 numbers. This is the advantage of coinciding or making your origin of the coordinate system coincide with the tail of all the vectors. How about the vector difference? Well, you have to wait for a few slides to see how to define the sum and addition of vectors when you have 2 different vectors here. Okay. But for now, please remember that you can draw a vector from the origin to any other point in the 2 dimensional space. All vectors are referred with respect to origin. Okay. So you have a vector A which is referenced with the origin O here, and let us say this vector A is terminating at a point 2.5 and 3. What does this 2.5 and 3 mean? If you forget the vector A, this simply gives you the location of the point 2.5 and 3 in the 2 dimensional space that is described by this vector x and y, correct. So I have a vector x and y, and all points are specified by 2 coordinates x. So in this particular case, the vector A goes from the origin and terminates at 2.5 and 3. Now to go from O to A, I can of course go along the red line, or I can go along the horizontal direction until I reach this point. You can see that where I am reaching this one, and then continue in the vertical direction. Now if you remember how we added 2 vectors, you had one vector tail origin, to that you added another vector, that is you brought in another vector by parallelly translating it such that the tail of the second vector coincided with the head of the first vector. Now I have a tail of this vector which is now getting added to the vector which is horizontal. So I have a horizontal vector, then a vertical vector. The sum of these 2 vectors is obviously the vector OA, which you can see very clearly over here. What are the 2 vectors that I am adding? The horizontal vector which is given by this blue line, and then a vertical vector which is given by this blue line. What is the magnitude of the horizontal vector? It is exactly this 2.5, and in which direction does it point? It points along the x direction. So, I can represent this vector itself as 2.5 x hat, right. This vector is 2.5 x hat, and this is precisely the vector that is giving you this horizontal vector. So, this horizontal vector is characterized by x hat a x, where x hat is the direction of the vector which is along the x axis, and a x is the magnitude of that vector, that is of the horizontal vector, which is 2.5. So, this is another way of saying that you move 2.5 units along x and then move 3 units along y, and if you move along y, you are actually creating a vector here which again is nothing but a parallelly translated vector y hat a y, and what is a y here? A y is 3. So, this original vector OA has been resolved or decomposed into two vectors, the sum of two vectors. Both these vectors are, so one of the vectors is along x, the other vector is along y. These two themselves are perpendicular to each other. You can see that from the graph, the vector Ax x hat is perpendicular to the vector Ay y hat. Okay. Similarly, as we defined a unit vector for the x axis, I can define a unit vector for the y axis, and I have actually used that definition of unit vector of the y axis when I am writing this vector y hat a y. Okay. So, the vector OA has been resolved into two components, that is sum of two vectors, one vector along x and the other vector along y. So, I have two vectors, one along x and one along y. The sum of these two is giving me the vector OA. Okay. Keep this in mind. Okay. Now, we move from 2-dimensional coordinate system to 3-dimensional coordinate system. Now, this is why electromagnetics is sometimes thought to be very abstract, mathematical and a tough subject, because you have to work with 3 dimensions. However, your work will be simplified if you understand the coordinate systems and if you choose an appropriate coordinate system for your problem. Okay. We will see the tragic consequences of choosing a bad coordinate system to solve a particular electromagnetic problem sometime later. For now, let us try to understand the 3-dimensional coordinate system. If you have followed the discussion of 1 dimension and 2-dimensional coordinate system, extending this to 3 dimensions should not be a problem, except that it will be little mentally taxing in visualizing a 3-dimensional vector. If you go back to 2-dimensional case, you had two lines, maybe we can take this as the 2-dimensional coordinate system example. So, you had two lines which were perpendicular to each other, and these two lines are mutually perpendicular to each other, and you define a unit vector along one and you define another unit vector along another axis. So, you have a unit vector x hat, you have a unit vector y hat. Okay. So, any point was actually given by intersection of two lines. For example, you look at this point 2.5 comma 3, this point at which the vector A is terminating is actually the intersection of two lines. This line, this horizontal line that is shown here, is the horizontal line which corresponds to the constant value of x. Okay. So, this line is x is equal to 2.5, whereas this horizontal line that I have shown here dashed is the line y is equal to 3. Okay. This line is x is equal to 2.5, you can actually stretch this along this direction, and no matter where you are on this point, the value of x will always be the same. The value of x along this dashed vertical line will always be same, and it will be equal to 2.5. The value of y along this horizontal line will be the same, and it will be equal to 3. Only thing is x will be changing in the horizontal line, whereas x will be constant here and y will be changing as you move up and down. Okay. So, any point in 2-dimensional coordinate system was represented as intersection of two points. Now, on a 3-dimensional coordinate system, you are looking at intersection of a mutually perpendicular axis which form 3 planes. Okay. What is this plane? See, now look at this x is equal to 0 plane. I have 3 mutually perpendicular axes. That means that axis x will be perpendicular to axis y will be perpendicular to axis z. Okay. Of course, axis z is perpendicular to axis x. Look at x is equal to 0 plane. Okay. All points on this plane have the x value which is equal to 0, and if you look at this horizontal plane, okay, this is z is equal to 0 plane, because all points on this plane have a constant value of z which is 0 in this case. Similarly, you have another plane which is y is equal to 0, you can go up, which means z is changing, you can go along the direction of x, which means x is changing, but you are not moving away from the plane, which means y is constant. So, you have y is equal to 0 or a y is equal to constant, in this case the constant is 0 plane, you have x is equal to 0 plane, you have z is equal to 0 plane, and the intersection point of all the 3 planes defines the origin. Now, if I want to specify a general x, y, z point, how do I specify? Well, you have to put up 3 mutually perpendicular planes there. You have to put up x is equal to constant plane, y is equal to constant plane, and z is equal to constant plane. So, you have to put up 3 mutually perpendicular axes composed of 3 different planes, okay, so as to specify any point. So, clearly any point in a 3-dimensional space will have to be specified by 3 points. Okay. Note the direction of the vector arrows over here. I have a vector x which is increasing in this direction, I have a vector y which is increasing in this direction, and I have vector z which is increasing in this direction. Okay. The specific directions were chosen to satisfy what is called as right-handed coordinate system, such that the resultant coordinate system is right-handed coordinate system. What is right-handed coordinate system? Right-handed coordinate system is shown here. You imagine yourself as using your thumb finger to point along the z direction. Okay, so if you imagine yourself as using the thumb to point along the z direction, you will see that the index finger will be pointing along the x and the curled fingers will be pointing along y direction. Okay. So, you have thumb pointing along z direction and the index finger pointing along the x direction, and the curling is pointing along the y direction. The curled finger would be pointing along the y direction. So, in other words, if you go from x to y, you will be going up along the z direction. You can imagine a different coordinate system in which if you go from x to y, you will be moving along the minus z direction, okay, minus z with respect to this particular z I am talking about. That would be a coordinate system that would be looking like this. Okay. It would be an inverted coordinate system and sometimes called as the left-handed coordinate system. Let us look at how to specify the points on a 3-dimensional coordinate system. To specify a point which is x, y and z, okay, I need 3 planes. As I have just told you, I need 3 planes. So, if you look at this plane should be erected at x is equal to some constant, okay, whatever the value that is given to me, and this plane you can see here is to be erected at y is equal to constant. So, whatever the value of y that I need to specify, I have to put up a plane here. The intersection of the planes x is equal to constant and y is equal to constant will give me 2 coordinates x and y. To get the third coordinate, I have to now put up a plane which is z is equal to constant. Okay. So, 2 planes will give me 2 coordinates, the third plane will determine the final point or the final coordinate of the location in space. Again, you have 3 mutually perpendicular directions, which is one vector pointing along x, one pointing along y and one pointing along z direction. For example, consider point P and Q. Point P is -2, 2 and 3, which means that I have to put up a plane at x is equal to -2. X is equal to -2 occurs beyond this. For example, this is the x is equal to -2, and then I have to move to point 2 on y axis. So, I can actually move along the x line to the y axis to get me this point. Okay. This is equivalent of putting up a plane at y is equal to 2 and plane at x is equal to -2. The intersection of those two will be at -2 and 2. Now, if you move up, because this is 3, if you move up to the point 3 or the plane where z is equal to 3, you will end up with point P. So, to get to point P, you move -2 along x, 2 along y and 3 units along z. Similarly, to get to y, which is 3, -2 and 2, you have to first move along x is equal to 3, that is to move to the plane x is equal to 3. So, I move to this plane x is equal to 3. On this plane y and z values could be anything, but y is equal to -2 is given. So, I need to now move to y is equal to -2 plane. So, I need to set up y is equal to -2 plane. Now, when I bring these 2 planes together, I am at a point which is 3 and 2. Now, I have to move to point 2 along z. So, which means I have to erect a plane at z is equal to 2. So, I move to point 2. So, this q is defined by 3 numbers 3, -2 and 2. Okay. A different notation is to just give you the vector, I mean just give you the point p and give the coordinates of the point. So, p and in brackets you give the coordinates, say in this case it is -2, 2 and 3, and for q it would be 3, -2 and 2. Okay. So, this is how to specify locations on a 3-dimensional coordinate system. I hope that you have understood this particular point, and I suggest that you try to graph more number of points to become familiar with this coordinate systems, okay, with this particular coordinate system.